Let's imagine that I have a reaction that involves A molecules plus B molecules to form A plus B molecules. And this reaction is an equilibrium reaction. What would happen if I start the reaction with only A and B present? Initially, we start to make some AB molecules. And at some point, we make a number of AB molecules, and then the reaction continues to occur in both directions so that every time an AB molecule falls apart, we form an A and a B, and then another A and B get together to form another AB molecule. And so as initially we have only A and B, we make some AB until we get to the point where we're at the constant concentration of AB that is required at equilibrium and the constant concentration of A and B that is required for the equilibrium of this reaction. And at that point, the reactions continue to occur in both directions, but every time we make an AB, we have an AB fall apart to form reactants again. Notice that in this case, we have ended up with 3 B molecules, 3 A molecules, and 2 AB molecules. What would happen if we started the reaction with only AB present? Notice that this time the AB molecules have fallen apart to form some A plus B molecules. And when we get to the point that the number of AB molecules is equal to the constant concentration of AB required for this equilibrium reaction, we end up having the reaction happen in both directions so that every time one of these falls apart, we form an AB molecule from an A and a B in solution. Notice that regardless of whether we start with all AB or whether we start with A and B separated, we have ended up with 2 ABs, 3 A's, and 3 B's. This is a hallmark of all equilibrium reactions. No matter where you start the reaction, no matter how much reactant or product you have present, when you get to equilibrium, you will have a ratio of products to reactants that will remain constant. And so the ratio of products to reactants will be the same no matter how or where you start the reaction. And so this ratio is very important because it defines the equilibrium point for any given reaction. Because this ratio is so important in defining equilibrium reactions, we give it a special name and a special symbol. And so we call it the reaction quotient, Q, and it's going to be equal to a ratio of product concentrations divided by reactant concentrations. Notice also that this reaction has come to equilibrium, but there is not an equal number of products as there are reactants. And so a common misconception is that equilibrium means that there's the same amount of products as there are reactants, and that is simply not true. The number of products relative to the number of reactants tells us something about a particular reaction and how strongly it goes in the forward direction relative to how strongly it goes in the reverse direction. If the stability of the reactants is greater than the stability of the products, then the reaction is going to go much more likely in the reverse direction to form more stable reactants than products. And if the opposite is true, if the products are more stable than the reactants, then the reaction is going to go more likely in the forward direction, more strongly in the forward direction, to form more products because they are more stable. And so the value of this reaction quotient for any given reaction can be very different. Finally, let's look at what happens to the reaction quotient Q as a function of time. So in the first example, we started with all reactants and no products. And so at time t equals 0, we had concentration of products was equal to 0, and the reactants were some finite number, 5 times 5 equals 25, because we had 5A and 5B. And so you can see that at time t equals 0, Q was equal to 0 divided by 25, or 0. So we started out with a reaction quotient that was 0. As we began to approach equilibrium, we made more products, so the product concentration increased and the reactant concentration decreased. And so this ratio that between reactants and products is going to increase because the numerator will increase and the denominator will decrease, causing this ratio to increase. And so we end up increasing this ratio in time until we reach a point where we have the equilibrium amounts of reactants and products. So we have 2AB, 3A, and 3B, and at that point, their concentrations don't change, and so the ratio doesn't change. And so in time, we see that this Q value goes from 0 to a constant value when the reaction reaches equilibrium. If we look at the second example of Q versus time, we can see that we started with all products. We had 5 products at time t equals 0, and we have 0 reactants. And so this reaction quotient is undefined or approaches infinity at time t equals 0. And then as the reaction proceeds, we lose the AB, so we lose these products, and we gain A and B, so we gain the reactants in the reaction written this way. So in this case, we're starting with all AB, and so we have a lot of that, but no reactants, and so we have an undefined reaction quotient. And then we lose AB and gain A and B, so the numerator goes down, the denominator goes up, and so Q begins to decrease. And so we see a decrease in Q until we reach a constant equilibrium value. What it will be true is that the equilibrium value that I reach in this case, starting with all reactants, will be equal to the equilibrium value that I reach in the case where I started with all products. That value of Q, the value that is constant, so when I reach a constant value of Q, that value is called K, the equilibrium constant. So Q at equilibrium, so when I reach the equilibrium value of Q, we're going to call it K. And K will be the symbol for our equilibrium constant.